Welcome back to the Deep Dive. Today, we are exploring something really fundamental, the moment when artificial intelligence, well, it finally started learning
Yeah.
a bit more, like how we humans do. Just think about your own intelligence for a sec.
Yeah.
If you're trying to get your head around a complex topic, you don't just use one thing, right? Yeah.
Definitely not.
You read the text, you look at the pictures or diagrams, maybe listen to someone explain it, maybe jot down notes.
Exactly. All those different inputs, those senses, they combine, they work together.
Right, to build this single sort of cohesive understanding. But for years, AI, even the really advanced stuff, was kind of stuck in its own lane.
Yeah, you had AI that was amazing with text, like the early GPTs you mentioned.
Or others brilliant with images, like image recognition models.
But they didn't really talk to each other effectively. They were separate skills.
So our mission today is to explore that next leap. Multimodal AI. AI that uses multiple senses. And, crucially, to unpack the sort of secret sauce transfer learning that makes this incredibly complex tech actually practical for, well, everyone, not just those billion-dollar labs.
That's the key pivot, absolutely. Multimodal learning, as our sources frame it, is fundamentally about combining information from different modes, different sources.
Like sight and language.
Primarily vision and language. Yes, that's the main focus right now. The goal is to create an understanding that's, much richer than what you'd get from just text or just images alone.
It makes sense. If AI is going to reason about the world like a person, it needs to see the picture and read the caption, basically.
Precisely.
So comparing that old unimodal AI one sense only to this new multimodal approach,
Yeah.
it's a huge difference, isn't it?
Oh, night and day. Unimodal AI might identify an object in a photo, or it could write a sentence about that type of object.
But not connect the two directly.
Right. Multimodal AI bridges that gap. It does both together. Okay, let's unpack this. What can this AI actually do for you?
Yeah, let's get concrete.
Okay, two key examples really show the shift. First, image captioning. The model looks at a photo, let's say a really specific one, like a black and white dog chasing a bright red frisbee on a pebbly beach at sunset.
Okay, very specific.
Yeah, it doesn't just output dog. It generates that exact description. It understands the object's dog, frisbee, beach, but also the relationships, the environment, pebbly, sunset. It's seeing and describing.
That's already pretty impressive. What's the second one?
The second one really gets into reasoning, visual question answering, or VQA. This is where you give the AI an image, maybe something complex, like an X-ray, and then you ask it a specific text question about that image, something like, is there visible metal fragmentation near the distal tibia?
Right. Very technical language there.
Exactly. The AI has to look closely at the image, understand the specialized words in the question, and then put it all together to give a precise answer about a specific location in the image.
So it's combining sight and language to actually generate useful, targeted information.
That's it. Real utility.
And this combined power, it's not just theoretical, is it? You mentioned it's already changing things in big industries, like radiology.
Absolutely. In radiology, AI systems can now look at the raw X-ray images and combine that with the radiologist's own previous reports, clinical notes.
So it's reading the patient's history alongside looking at the current scan.
Yes. The AI doesn't just see the image in isolation, it reads the context. And this lets it do things like suggest diagnoses or maybe even more importantly, flag inconsistencies.
Like if the doctor missed something subtle.
Potentially, yeah. If the AI, having seen the visual evidence and correlated it with thousands of similar written reports, spots something suspicious the human eye might have glanced over, it can highlight it. An assistant, really.
That's huge.
Yeah.
And what about e-commerce? That affects pretty much everyone.
Oh, massively. Think about searching for, say, a specific type of running shoe. The AI isn't just matching the words you typed, like heel support.
It's doing more.
It's combining the product photos, the specs listed, the customer reviews, that's text, of course maybe the price, to give you better search results and recommendations.
Ah, so it learns patterns. Like people who search for strong heel support often click images with a certain look.
Exactly. Even if the text description doesn't explicitly mention that specific visual feature, it learns those cross connections, makes the whole shopping experience smarter, more intuitive.
Okay, so this multimodal approach, combining senses, seems obviously powerful, almost essential if we want AI to get closer to human understanding.
It really is necessary for that next level of perception and reasoning. But, and this is a big, building this technology from the ground up it's monumentally difficult.
Why is that?
Well, think about how much effort goes into training just a top-tier language model alone. It's already massive.
Right.
Now, try building one that handles both vision and language together simultaneously from scratch. It's almost impossible for most places. The biggest hurdle, data. You need absolutely enormous, perfectly aligned data sets.
Like meaning?
Meaning the image and the text description or the video frame and the audio transcript have to match up exactly, and you need billions of these pairs. Billions.
Billions. Okay, that's the data hurdle. What about the compute side? We hear astronomical costs. What does that actually mean? How expensive are we talking?
We're talking costs that can easily run into tens, maybe even hundreds of millions of dollars.
For one training run?
For one training run, yeah.
Yeah.
The sources aren't exaggerating with astronomical. You need these huge clusters of specialized chips, thousands of top-end GPUs running flat out for weeks, sometimes months.
Wow.
So realistically, only a handful of the biggest players OpenAI, Google DeepMind, Meta, can actually afford that kind of infrastructure, the power bill, the whole setup for these giant foundational models.
So if that was the only way, this tech would just stay locked up in those big labs.
Yeah, pretty much. It wouldn't be accessible to your average company or startup.
Okay, here's where it gets really interesting then. How does this amazing tech break out? How does it become practical for the rest of us?
This is where transfer learning comes in. It's honestly quite ingenious. Instead of starting from absolute zero, which, as we said, is financially crippling for almost everyone, you start with a pre-trained multimodal foundation model.
Meaning a model one of the big labs already built and trained.
Exactly. It's already crunched those billions of data pairs. It already knows fundamentally how to link vision and language. Your job then becomes much, much smaller.
You just adapt it.
You adapt that huge existing knowledge base to your specific, maybe niche task.
So we get to stand on the shoulders of giants, basically.
Yeah.
Use their massive investment without having to repeat it.
That's the core idea. And we're seeing some well-known models emerge that are built for this.
Listeners might recognize some names here, like CLIP.
CLIP from OpenAI, yeah.
Right.
Trained on, 400 million image text pairs scraped from the web. Just a mind-boggling amount of data.
And it's famous for zero-shot classification. What does that mean in simple terms?
It means it can classify an image based on a text description you give it, even if it never specifically saw that exact category during its training. You just describe what you're looking for in text.
Okay, powerful. What else?
Then there's Flamingo from DeepMind. That one's known for being really good at few-shot learning.
Meaning it learns new things quickly.
Yeah, it can adapt to a completely new task with just a handful of examples, which makes it super efficient if you need to deploy something fast.
And one more you mentioned earlier, Elevate.
Right, Elevate. Large language and vision assistant. That one specifically connects a language model, the part that talks with a vision encoder, the part that sees.
To create those multimodal chatbots we talked about. The ones that can actually look at a picture you upload and then talk to you about it.
Precisely. That's Elevate enabling that kind of interaction.
So the real win with transfer learning is avoiding that massive upfront cost.
That's the practical payoff, yes. You don't need billions of training samples anymore. A startup working on, say, agricultural drones.
Right.
They could fine-tune a model like CLIP specifically to spot crop diseases from drone images. Or an e-commerce site could adapt a model like Pally for really specific, nuanced product searches across different languages.
Without needing $100 million for the initial training.
Exactly. They skip that crippling cost, but still get really high performance tailored to their specific need.
Okay, so transfer learning is the key. But how does it actually work?
Yeah.
Adapting these massive models must still be tricky, right? You can't just retrain the whole thing easily.
No, you're right. The foundation models themselves are huge, trillions of parameters sometimes. So just fine-tuning the entire thing end-to-end is often still too much compute for many. The sources highlight some clever, really efficient strategies that focus the training effort.
Let's try and make sense of these using those analogies we found. So imagine the big pre-trained model is like a team of super smart general experts. You get a vision expert, like a photographer.
Sees everything.
And a language expert, maybe a librarian or writer.
Knows all the words.
And our goal is to get them to work together on a new specific job, like understanding medical x-rays, which wasn't their original training.
Okay, good setup.
So the first strategy is called freezing the backbone. This sounds like a really common, cost-effective way.
It is. Very popular. Here, you keep the core experts, the vision expert, and the language expert completely frozen. untouched.
So they keep all their general knowledge about dogs, cats, text, grammar, everything.
Everything. You only train the bit in the middle, the layer that connects them and fuses their knowledge. That's called the cross-modal layer.
So in the analogy, it's like using two established experts, but only training the translator who helps them talk.
Exactly that. The original experts still know what a cat looks like and what the word cat means, but now the translator learns how to combine their general knowledge to specifically identify and describe, say, a suspicious lesion on an X-ray using the right medical terms.
But wait, if we keep the main experts frozen with only their general internet knowledge, doesn't that limit things? What if my new task is really different? Like, say, applying it to weird microscopic images instead of cat photos.
That's a fair question, and it is a trade-off. But the thing is, models like CLIP or Alave were trained on such incredibly vast and diverse data.
Right, 400 million pairs for CLIP.
Yeah, so they've learned really fundamental concepts about shapes, textures, structures, and how language connects to those visual ideas. Freezing the backbone works because you're tapping into that deep, general understanding. You're just teaching the translator how to map that general knowledge onto your specific domain's terms and visual patterns.
Okay, so it works well if the new task isn't completely alien to the original training.
Generally, yes. If there's some semantic overlap, it's remarkably effective and very efficient.
Got it. Okay, second strategy. Prompt-based techniques. This sounds different. You're not retraining anything.
Not the model's internal weights, no. Instead of changing the experts, you guide their existing knowledge using carefully crafted text prompts.
So this is the asking the right question instead of retraining the expert idea.
Precisely. The model already understands the link between vision and language deeply, so you can phrase your request in just the right way to get the behavior you want.
Like instead of just asking it to classify an image, you give CLI AP a prompt, like a photo of a specific type of bird is shown here, and make it match the image to that specific prompt.
Exactly. You're steering the model's existing capabilities with language. Very flexible.
Okay. And the third main strategy, something called LoRa on adapters. This sounds a bit more involved, but maybe more powerful.
It's arguably the most elegant recent approach, yeah. It aims for both high performance and efficiency. LoRa stands for low rank adaptation.
Low rank adaptation, okay.
So instead of retraining the whole huge model or even just the translator layer, you insert these tiny extra modules, the LoRa adapters, directly into the pathways of both the vision and the text experts.
Like little plugins.
Kind of like lightweight plugins, yeah. You keep the main experts frozen, but you only train these small new add-ons.
Okay, so if freezing the backbone only trained the translator between the experts, LoRa is like upgrading both experts with lightweight add-ons instead of retraining their whole brains. Is that the idea?
That's a perfect way to put it. You get to slightly adapt both the vision expert and the language expert, making them better suited to your specific domain, but you're only training a tiny fraction of the total parameters.
Which means it's much easier on memory and compute power.
Incredibly efficient, yes. Often giving performance close to full fine-tuning, but at a fraction of the cost.
Wow. Okay, so these strategies, freezing, prompting, LoRa, there would actually make transfer learning work in practice.
They're the key techniques that let us take those giant foundation models and specialize them effectively. And we're seeing concrete results now because of this.
Moving beyond theory into real applications.
Definitely. Look at healthcare again. We're seeing domain-specific models like MedCLP.
So CLP adapted for medicine.
Exactly. Specifically trained to align complex medical images, MRIs, CT scans, you name it, with huge collections of specialized radiology reports.
So it learns the language of doctors alongside the images.
Yes, it learns the complex medical jargon, the descriptions of pathologies, and the visual patterns that correspond to them. It becomes a genuine assistant that can highlight suspicious areas, maybe even suggest possible diagnoses based on both what it sees and the written history.
That's amazing. What about outside medicine? Education, maybe?
Yeah, EdTech is another interesting area. Imagine multimodal AI looking at a complex diagram like the human heart or an engine schematic.
Okay.
And it combines understanding that visual layout with a text question like, where does blood flow after leaving the left atrium? Or point to the combustion chamber.
So it understands the diagram and the question about it.
Right. It blends visual and textual reasoning. This could lead to really smart tutoring systems that can assess if you understand a diagram, not just if you can answer a text question.
Very cool. And just to quickly recap the foundation models enabling this, CLIP is great for that zero-shot classification.
Yep, describe something in text, and CLIP can find it in images.
And LVA is the key for those chatbots that can actually see and discuss images with you.
That's the one enabling those visual conversations.
So, stepping back, if we connect all this to the bigger picture, multimodal AI is really about giving machines senses that work together.
That's a great way to think about it. Instead of just sight or just language, it's giving them sight and language and the ability to reason across them. A more holistic kind of intelligence.
So what does this all really mean for you listening to this? What's the main takeaway?
I think the crucial point is that transfer learning is the great enabler here.
The thing that unlocked it all.
Yeah. It took this incredibly powerful multimodal AI, which required those astronomical investments to create initially, and brought it out of the ivory towers of the giant research labs.
Through clever tricks like freezing parts or adding LoRa adapters.
Exactly. Those strategies made it practical. Now, startups, researchers, regular companies, they can actually use this power to solve specific real-world problems without needing a billion-dollar budget. It democratized it.
Yeah, it's a huge shift.
It is. And we've mostly talked about aligning text and static images today because that's where a lot of the progress has been clearest. But the next big frontier, mentioned in the sources, is bringing in sound and video.
So not just reading text and seeing pictures, but hearing audio and watching video.
Imagine AI that doesn't just process the words spoken in your next video call,
Okay.
but also analyzes how they're said, the tone, the emotion, and the voice from the audio, and understands what's happening visually on screen, the shared diagrams, the gestures, the expressions, all integrated all at once.
Wow, okay, that's another level entirely.
What new things become possible when transfer learning helps AI master video audio text, understanding the way it's now mastering image text? Think about how different social media could be, or collaboration tools, or even entertainment.
That complete sensory integration. That's the future these techniques are unlocking.
That's the direction things are definitely heading. A much richer, more integrated AI understanding of the world.
A truly fascinating thought AI learning to listen, watch, and read all at the same time. Thanks for diving deep with us today.
My pleasure.
We'll get you on the next deep dive.